Last time in 1.3, we went over the basics of probability, so now let's start working on an example problem in regards to probability. Suppose someone drops a rock off a cliff of height h. As it falls, I snap a million photographs at random intervals. On each picture, I measure the distance the rock has fallen. So our question is, what is the average of all these distances? That is to say, what is the time average of the distance traveled? So let's just begin by sketching this out. So we have some sort of cliff. It has a total height of h, and our rock begins up here, and let's set the coordinates to be x. So at the top, x equals 0, and positive x hat goes down. So as the rock goes down, x becomes larger. So let's think. Is this a discrete probability distribution or a continuous probability distribution? And hopefully that the answer to that is obvious. This is a continuous probability distribution. I cannot define exactly the location of the rock at any given time because there's no limit to how far I want to take my accuracy. I can go down to meters, millimeters, centimeters, nanometers, etc., etc. So instantly, we can define the equation for the average of x and say that the average distance that the rock has fallen is equal to the integral from 0 to h, which are the bounds of this problem, of x times our probability distribution rho of x times dx. So ultimately, kind of what our problem boils down to is mainly just trying to find what rho of x actually is. Well, kind of to start this, let's consider this instead. I've taken a million photographs at random. So what is the probability of selecting one of those photographs out of the million at random? So let's say that it takes a time interval dt to snap a photo. So then, if it takes us some time interval dt to snap a photo, if the photos are all taken randomly, then the probability of randomly selecting a given photo out of my 1 million photographs, probability to select a random photo, well, that probability is going to be just dt, which is my small time interval, divided by the total time that it takes for the rock to hit the bottom of the cliff. So where t is the total time the rock falls for. Okay, well, let's try to kind of find what t actually is before we go any further. So we know from kinematics that we can define the fall of the rock using the function x equals x0 plus v0 times x plus 1/2 times acceleration times t squared. And we know that the rock starts at 0, and we also know that it starts at rest, so x0 and v0 both equal 0, so x just equals 1/2 times acceleration, which is g times t squared, where I've removed the negative from gravity because we're defining the downwards direction to be positive. In that case, to find t, what we can say is, okay, well, the rock falls a total distance h, so h is equal to the distance fallen at time big T squared. And if we kind of rearrange this, then we get that t equals the square root of 2h over g. Okay, so if we plug this to the top, then our probability ends up being dt times square root of g over 2h. So what is this? This is equivalent to our probability. Now, note that the probability in a given distribution is the discrete analog to the probability density, which is found in a continuous distribution. So evidently we're actually pretty close to the answer. It's just kind of in the wrong form, because what we want is rho of x dx, but currently we have some function in terms of dt instead. So our goal now is we want to convert p of t into rho of x. And one way that we can actually do this is we can recognize that dt is a time element. So one way that we can kind of link the time element to a position interval is we can actually use velocity, because we know that v equals dx over dt. So one thing we can do is we can rearrange dt to say that dt equals dx over v. And if we did decide to do this, then plugged it back up into here, this actually would give us a probability distribution in terms of dx. So let's actually do that. We know what x of t is already from the kinematic equation over here. X equals 1/2 gt squared. So if we just derive it with respect to time, then we know that v equals g times t. And since we know that v equals gt, what we can do is we can plug this in, and what we get here is dt times square root of g over 2h is equal to dx over v times square root of g over 2h, which is then equal to dx over gt times square root of g over 2h. So now we have a function of the form dx times some function of t. And this is closer than what we got before, but it's still a little bit off, because what we need is actually something of the form dx f of x. And this clearly does not equal that. So we need to find a way of converting our t variable into an x variable. Well, if we look back here, we know that x equals 1/2 gt squared. So if we take it, we can kind of take advantage of that and say, well, okay, x equals 1/2 of gt squared. So if we isolate t, we get t squared equals 2x over g, or t equals square root 2x over g. And we can plug that in up here. So let's do that. So we have dx over gt times square root of g over 2h. And if we set t, then we get this equals dx, and then we're going to simplify the g, so we get dx square root of g times 1 over square root 2h, and then times square root of g over 2x. Okay, so this equals dx, the g's cancel, the two root 2's go outside of the square root, to square root of hx. And this is, in fact, in the form of something that we require. So this equals f of x dx. And this is the exact form we need, so we actually do have rho of x dx now. So from here, we can just kind of plug this in. because we already know what our solution is, or the form for our solution. We already know that the solution for the average of x is equal to the integral from 0 to h of rho of x dx, or x times rho of x dx. So this equals x, the integral from 0 to h of x divided by 2 square root of hx dx. And then from here, we can kind of just plug this into a calculator, and what this will give us is h over 3. So let's do some sanity checks. First off, we said that the average of x. First off, one of the requirements we made is that x had to be less than h over 2. H over 3 is less than h over 2, so that does check out. Our second condition is that this is a probability density, so we can check whether or not our answer makes sense by setting an integral from 0 to h of rho of x dx, and that has to equal 1. So we can do that right now. We can say an integral from 0 to h of our rho of x dx, which is 1 over 2 square root of hx dx, and if you plug this into a calculator, this does indeed equal 1, so this is also met. So we're reasonably confident that our answer is correct. H over 3 is in fact the average distance that the rock has traveled. Now, another thing that we can do is we can actually graph our probability density function to kind of get an idea of what the probabilities look like. So we can graph rho of x to see what the density looks like. And if we do decide to do that, which we will do right now, we know that rho of x, let's just write it again, is equal to 1 over 2 square root hx, and that this is valid between 0 and h. So if we were to kind of graph this, you could do this along in like maybe Desmos, for example. The resulting graph looks something like this, where if this is our 0 and then this is our h, this is 1 over 2h, and this is our x-axis, and this is rho of x. The resulting graph looks something like this. Whoops. Resulting graph looks something like this. So evidently, there is a higher chance of finding our rock at any given random photograph to be closer to the top of the cliff compared to at the bottom of the cliff. And one thing I would like to note here is actually, once again, the properties of continuous distributions. Note that this kind of probability density goes up to infinity as we go to 0. That does not mean that there's an infinite probability of finding our rock at 0. Because remember, the probability of finding the rock at a specific value, such as this value or this value, is actually 0. Because what we're finding is the area under the integral. So because of that, what we say is that there's a very high chance of finding the particle in this sort of early interval here. And there's a very low chance of finding it somewhere out here in the outer interval.